I'm not exactly sure why we go from dipoles, dipole moments. We're going to learn how to draw those, but then your book takes a break and talks about isoelectronic series. So I'm going to go along with the book and take a small break from the whole dipole is the molecule polar thing and talk a little bit about isoelectronic series. So I made some small changes here to your packet, what I would present that you have in front of you. So be patient with me on these. You can write on it. It's similar to, not identical to, what's on your packet. So first we have to write the electron configuration for oxygen. And you can use the shorthand for this. That's not a problem. I'm going to change my pen color. Red's not great for this. Okay, so for oxygen then, let's see, finding oxygen. There. So we're going to do helium. There you go. Now, that's easy enough. You should be able to do that. But for the oxygen ion, so we have to start thinking about what it takes to be an ion. And the first thing that it takes to be an ion is figuring out the charge on oxygen. So you should know oxygen as an ion looks like that. Well, what does this -2 mean? It's all about the electrons, of course, because chemistry is all about the electrons. So is the electrons for oxygen, did it gain electrons? Or did it lose electrons? Well, if you said gain, you are correct. Yay! It gains electrons. How many does the oxygen ion gain? Well, it gains 2. So let's take a look at the oxygen configuration. In order for it to gain 2, where do those 2 electrons go? That's right. They go there. We added 2 to the 4. So the oxygen ion is exactly the same as neon. That is the electron configuration for the oxygen ion because we added 2 to the p orbitals. So we need to write the electron configuration for the magnesium ion. And the way I do this is I start off with the magnesium atom. Oh, I didn't need that. We'll start here, magnesium. So starting from the previous noble gas, we have neon. Then 3s2. Oh, that's it. Now, the ion. What is the charge on the magnesium ion? That's correct. It's 2+. What does that 2+ mean? Did it gain electrons? Or did it lose electrons? It lost electrons. That is correct. It lost. How many electrons did magnesium have to lose? Correct. It had to lose 2. And where is it going to lose those electrons from? The 3s orbitals, you are correct. These guys go, these guys are empty. So the magnesium ion electron configuration looks like this. So to write the electron configuration for the carbon ion, well, I like to start with writing the electron configuration just for carbon. And carbon is 1s2. You can do shorthand, but I think that's just as easy. And then we have 2s2 and 2p2. Now, take a look. Ion. What does it mean for carbon to be an ion? The charge on carbon is 4-. So the ion actually, does it gain or lose? That's right, it gains electrons. How many does it gain? Remember, to be an anion, you have to gain electrons. So it gains 4 electrons. Where are you going to put them? That's right, 2 + 4, 6 electrons. Who has this electron configuration? We said neon. You are correct. So the electron configuration for the carbon ion is the same as neon. Sorry about that. It's like the electrons rule. And so the atom puffs up and the ion gets bigger. Oxygen, it went from 8 protons and 8 electrons. And now look at it. It has 10 electrons. It can't possibly hold all of those electrons and orbitals together, so the atom gets bigger. As a rule, the more you gain, the bigger you get. Well, snap, that makes perfect sense. Like, think about weight. The more weight you gain, the bigger you get. Because that nuclear charge can't hold it nearly as tightly. As you go down the periodic table, yes, the ions get bigger just like the atoms get bigger. As you have more and more electrons, more protons, well, the protons don't matter that much, but you have more and more electrons, more orbitals, they all get stacked in there. However, the anion is always bigger than the atom. The metals will, of course, then do the opposite, because that's the way things work. If one does one thing, the opposite does the opposite. Well, I know that made perfect sense, right? Well, anyway, let's take a look at this alkali metals. Lithium has 3 protons and 3 electrons. To become an ion, what happens to lithium's electrons? Let's see, we've got lithium. It's 1s2, 2s2. It's not even 2s2. I got carried away. It's 1s2, 2s1. That is correct. Well, in order for lithium to become an ion, it wants to be like the nearest noble gas. And that's the nearest noble gas, the 1s2, helium. It has to lose an electron. This guy's got to go. No more of you. So then lithium ends up with 2 electrons. The nuclear charge is now stronger, and it can pull those orbitals in more tightly. So cations are always smaller than the atoms from which they come. Sodium loses 1 electron, so its effective nuclear charge goes up, and this nucleus can hold those orbitals in that much tighter. Sodium's electron configuration is 1s2, 2s2, 2p6, 3s1. This is exactly the same as who? Neon. So the sodium ion, in order to be a positive ion, you have to have lost an electron. Are you positive? Yeah, you got to lose that guy. This guy's got to go. So the sodium ion ends up with the electron configuration of neon. It loses an electron because it lost the effective nuclear charge on sodium, goes up. It now has more protons than electrons, and it pulls that cation in smaller. So the rule, cations always get smaller, and remember from the previous side, anions, they always get bigger. Here comes the big word, isoelectronic. Do you remember what the prefix iso means? Iso means same. And electronic, well, we're talking about electrons. The prefix "ic" just makes it a noun. Every single one of these ions has exactly the same electron configuration. They all have the configuration for neon. But look at their sizes. Why do you think that if each one of these guys has the exact same electron, well, neon's obviously neon, has exactly the same electron configuration as neon, why is oxygen so much bigger? Well, if you said effective, nuclear, charge, you would be correct. See, oxygen has 8 protons. As an ion, it has 10 electrons. There's no way that nucleus can hold on as tightly. No way at all. Fluorine has 9 protons, and here we have 10 electrons. And so fluorine, well, it does a better job of holding on to those orbitals. I kind of stumbled to those orbitals. And so it pulls it in a little smaller. So if you have an isoelectronic series where they all have the same electron configuration, the more the charge, the bigger it gets. Why? Well, because the effective nuclear charge goes down. Now, neon's neon. But look at sodium. Sodium is smaller yet. But look, it has 10 protons. Well, I can't talk. It has 11 protons for every 10 electrons. So its nuclear charge goes up, and it can pull this in more tightly. And look at magnesium. 12 protons for 10 electrons. It pulls it in more tightly. So we kind of have a rule here for isoelectronic series. So on the negative side, the more you gain, the bigger you get. And on the positive side, the more you lose, the smaller you get. Wow, that makes perfect sense. Think about weight loss. You gain weight, you get bigger. You lose weight, you get smaller. It's kind of the same idea, except this time it depends on the effective nuclear charge more than it depends on actual willpower. Okay, for the sodium ion, I like to start with just sodium, and I know I have it on a previous page, but go ahead and give it a try anyway. So sodium, it starts with neon, and then we have 3s1. The charge on sodium is +1. So what does that mean? Gain or lose? Yep, it lost an electron, so that's the one that's got to go. That valence electron that's a valence electron. It's out of there. So there's the electron configuration for sodium ion. Now we got to find anyone that's isoelectronic with this guy. Well, magnesium would work. But that's not an element. That's an ion. So we can't use that. How about neon? Is it isoelectronic with neon? Yay, yes it is. That is the element for which sodium ion is isoelectronic with, to mess that up. But anyway, it's neon. If I was looking for an ion, magnesium would have worked. Pause the video and see if you can come up with the electron configuration for the phosphorus ion. I'm going to go ahead and do it. I'm assuming you paused it. Well, phosphorus, we know, is going to start with helium. That makes 2s2 and 2p3. Now for the ion, phosphorus becomes 3 negative. So in order to become 3 negative, to gain electrons, to become more negative, we have to add 3 electrons to that guy, which becomes 2p6. So the electron configuration, if I wanted the full thing for phosphorus, would be what's above. But who has this electron configuration? Our old friend neon. So the phosphorus ion is isoelectronic with which element? Yay! Yep, you got it. It's neon. So we need the electron configuration for the chlorine ion. Go ahead and pause the video and see if you can do it. Let's see, chlorine by itself has the electron configuration of neon, and then 3s2 and 3p5. Now for chlorine to become an ion, what has to happen? Well, chlorine then gains an ion. So if chlorine gains an ion, we've got to add 1 to the 5. That becomes 6. So chlorine's electron configuration is neon 3s2, I said the chlorine ion, I really did, to 3p6. Who has this electron configuration? Well, if you said argon, you got it. However, that's not our answer. We need 3 ions who are isoelectronic to chlorine. What 3 ions would have the same electron configuration as argon? Well, sulfur certainly would. See, sulfur has an electron configuration of neon, and then it's 3s2, 3p4. What's the charge on the sulfur ion? Well, it's 2 negative. We had to add 2 electrons there. Oh, look, it's the same thing as argon. Let's try another one. How about phosphorus? Phosphorus's electron configuration is neon, 3s2, 3p3. What's the charge on phosphorus? 3 negative. So we had to gain 3 electrons. Oh, we have the same thing as above. Both of these would have the same electron configuration for argon. Let's try one more. Let's be creative and go with potassium. So what is the electron configuration for potassium? Well, that's argon. And then we have 4s1. The potassium ion loses an electron. I've lost an electron. Are you positive? I am. This is the one that has to go. Goodbye. Argon, then, is the electron configuration. We've now found 4. For extra credit, find 2 more. Okay, I'm telling you, you gotta know, you absolutely gotta know how to do these. Make sure you understand how to really make sure. Arrange these ions in order of increasing size. So that means increasing, we're going to go from small to large. From the previous slide, you should know that all 4 of these are isoelectronic. And really, you can't compare well unless you're looking at an isoelectronic series. Iodide, well, that guy's just going to be huge. I mean, look at all of the electrons it has. And it is just huge. So we know this guy's going to go on the very end. But who's the smallest? Who loses electrons? Remember, cations are always smaller. Always. So let's look at the 2 cations. We have magnesium and we have potassium. The more you lose, the smaller you get. So who's the smallest? Magnesium. Magnesium is smaller than potassium. All right, now let's look at sulfide and chloride. Remember, anions always get bigger. Okay, so chloride has a -1 charge. Sulfide has a 2 negative charge. Who gained the most? Who gained a little? Well, chloride only gained 1, so it's got to be smaller than sulfide. Sulfur gained 2, so it's bigger than chloride. And then, of course, we have this oddball iodide, which is, just ginormous. Make sure you know how to do a problem like this. Up next, One of my favorites, Lewis dot structures. They're fun to draw. Really, they are.